So we're looking at power series, which are polynomials of infinite degree. A polynomial of degree n looks like a0 plus a1x plus a2x squared, and the highest term is at most degree n. And if we have two polynomials, we add them just by adding the coefficients of the corresponding powers of x. So a0 plus b0 plus a1 plus b1x plus a2 plus b2x squared, and so on. That's how you add polynomials. And how do you multiply polynomials? F of x times g of x. Well, you're looking at all expressions of the form ai x to the I, when you distribute across, times bj x to the j over all I and j. So this is all expressions of ai bj times x to the I plus j. And if you collect all the powers of x that are the same, so what is the coefficient of x to the k? It's the sum of all ai bj, where I plus j is equal to k. So if you think about this for a minute, let's say f of x were 2 plus 3x plus 7x squared, and g of x was 1 plus 4x minus x squared. If you multiply them, you get all possible combinations, right? This is just distribution. 2 plus 3x plus 7x squared times 1 plus 4x minus x squared. What do you get? You get 2 plus 8x minus 2x squared plus 3x plus 12x squared minus 3x cubed plus 7x squared plus 28x cubed minus 7x to the fourth. And then when you collect all the constant terms, there's only one of them. All the terms that involve an x, looks like there are two of them. All the quadratic terms, looks like there are three of them. Minus 2 plus 12 is 10 plus 7. And the cubic term, there's only one of them. Only one? No, there are two. Minus 3 plus 28. You get a cubic term from 7x squared times 4x, that's 28, x cubed, and 3x minus x squared is minus 3x cubed. So you get 25x cubed minus 7x to the fourth. That's how you multiply polynomials. And power series are exactly the same. So a Taylor series, an infinite series, you might have f of x is a0 plus a1x plus a2x squared, but it goes on forever. Summation, let's say I goes from 0 to infinity, a sub I, x to the I. Well, let's use n, the subscript n, an, x to the n. And if you have another power series, b0 plus b1x and so forth, summation, n goes from 0 to infinity, b sub n, x to the n. If you add them, you just add the corresponding coefficients of x to the n, namely an plus bn. And if you multiply them, we have the same thing we saw in the case of polynomials. What is the coefficient of x to the n? You take the sum of all ai bj where I plus j equals n. That's the coefficient of x to the n. So this is the algebra of power series, and it takes a little bit of time to become fluent in manipulating them, but that's what you have to do. And power series come up for us when we're trying to solve a differential equation that we don't know how to solve explicitly. So it can happen that the only way to solve a differential equation is to look for a solution that is a power series.
Recorded.
Okay. Any questions about this? This is just sort of warm up. So chapter 7, section 1 is about just the algebra of power series. And we're going to look for power series that solve differential equations, which means we have to know the derivative of a power series. And just as for a polynomial, you differentiate a polynomial term by term, it's the same for a power series. If f of x is this power series, f prime of x is just what you get by differentiating each term. So the derivative of x to the n is n x to the n minus 1. And of course, when you differentiate the constant term, you get 0. So when n is 0, this is 0. So this really starts with 1. And of course, if you like to have the powers of x being n and not n minus 1, you can just shift the subscript here, replace n by n plus 1, and you get summation n plus 1, a n plus 1, x to the n, and now n does go from 0 to infinity. And if you take the second derivative, f double prime of x, you just differentiate each term twice. So the derivative of x to the n is n x to the n minus 1. And when you differentiate this a second time, you get n minus 1 a sub n x to the n minus 2. That's the second derivative. You just using the fact that you have x to the n. The first derivative is n x to the n minus 1. Second derivative is n minus 1 x to the n minus 2. So that is the whole background we need from power series. There's a lot more one can say about power series, and it's discussed in detail in section 7.1. And you really need to work it through carefully. And if you have questions, then definitely ask me. So here is a kind of warm-up exercise, but it indicates a lot about how we use power series to solve a differential equation. So let's say we have a power series, function y, which is summation a sub n x to the n, and goes from 0 to infinity. And we want to express two minus x y double prime plus 2y as a power series. So here's y. Y prime is summation n a sub n x to the n minus 1. Y double prime, differentiate again, you get n minus 1, a sub n x to the n minus 2, and goes from 2 to infinity.
Professor, can you bring the paper down?
Oh, sorry. So here we have a power series, and I want to express, so y is the power series. And here I have this expression 2 minus x y double prime plus 2y, and I want to write this as a single power series. So here's y as a power series. I differentiate it term by term once, I get this. I differentiate term by term a second time, and I get this. And if I want to shift the, no, actually, I'll just leave it like this for the moment. So 2 minus x y double prime plus 2y is 2 minus x times y double prime, that's this series, plus 2y, that's 2 times summation a n x to the n. And let's just expand this a little bit. So this is 2 times this series minus x times this series. When you multiply this series by x, you get n minus 1, a sub n, x to the n minus 2 times x is x to the n minus 1. Plus this. And now, in order to be able to collect the terms efficiently, what I want to do is write everything in terms of just x to the n. Instead of x to the n minus 2 and x to the n minus 1, I want x to the n. So I need to shift my series. So if in this series, if I replace n by n plus 2, I get 2 summation n plus 2, n plus 1, a sub n plus 2, x to the n. You see, it's the same terms because for every, if whatever is the exponent of x, this is 2 greater, and this is 1 greater, n plus 2, n plus 1, a sub n plus 1. In this series, I replace, I can think of it this way, I can replace n by n plus 1. I get minus summation n plus 1 times n, a sub n plus 1, x to the n. And in this series, I don't have to do anything. So now I have 3 power series that I'm basically adding and subtracting, and I just collect the coefficients of x to the n. This is summation, n goes from 0 to infinity. And what is the coefficient of x to the n? Here it's 2, n plus 2, n plus 1, a sub n plus 2, minus n plus 1 times n, a sub n plus 1, plus 2, a sub n. So we get this expression. And that's what our power series is. 2n plus 2n plus 1 a sub n plus 2 minus n plus 1 n a sub n plus 1 plus 2a sub n. Now, here is the connection, or a connection, to ordinary differential equations. Suppose we want to solve the homogeneous second order linear differential equation 2 minus x y double prime plus 2y equals 0. So this is not a second order equation with constant coefficients, and we don't have any obvious way to solve this equation, but we can look for a solution in power series. So if we let y be summation an x to the n goes from 0 to infinity, the question is, can we find numbers a1, a0, a1, a2? Can we find the coefficients of this power series so we get a solution of this equation? But if we let y be this power series, we just saw that 2 minus x y double prime plus 2y is equal to this series. And we want this to be equal to 0. But the only way a power series is equal to 0 is if every one of the coefficients are 0. So that means, what is the coefficient of x to the n? 2, n plus 2, n plus 1, an plus 2, minus n plus 1, n, an plus 1, plus 2an. This has to equal 0 for all n. And how do we find the solutions of this? Well, this is a recursion. This says that if you know an and an plus 1, 2 times n plus 2, n plus 1, an plus 2, has to equal n plus 1, n, a sub n plus 1, minus 2 an. Or an plus 2, divide by this, is n times n plus 1 over 2 n plus 2 n plus 1 a sub n plus 1 minus 2 over 2 n plus 2 n plus 1 a sub n. So the coefficients have to satisfy this recursion. These cancel and these cancel. So this is going to be equal to n over 2n plus 2 an plus 1 minus 1 over n plus 2 n plus 1 a sub n. So if you have any values for a0 and a1, this tells you a2. And when you have a1 and a2, this tells you a3 and so forth. So we have a recursion that explains to us or describes what the solution of this differential equation is in terms of a power series. You define the numbers, the coefficients by this recursion, and you're done. Now, what is definitely the case is that there is a lot of algebraic manipulation involved in solving these problems. And there really is no way to avoid it sometimes. You just have to do a lot of work. Right? What I just did was one of the examples in section 7.1. Example 7.1.6 on page 314 and 315. Let me do another example. And I'm going to take examples from the books. So when you're studying at home, it's easier, I think, to follow. So this is example 7.1.7 on 315 and 316. Suppose we have a power series which is centered at 1 and not at 0. So that means our power series looks like summation and goes from 0 to infinity a sub n, x minus 1 to the n. And we want to express 1 plus x y double prime plus 2x x minus 1 squared y prime plus 3y. So we want to express this as a power series in x minus 1. So again, this is y. Y prime is summation n a n x minus 1 to the n minus 1. And y double prime is summation n minus 1 a n x minus 1 to the n minus 2. So these are our 3 power series. And what we need to do is plug them into this expression, shift the indices as necessary. So you have powers of just of x minus 1 to the n, and collect the terms. So 1 plus x, so what is this equal to? This is 1 plus x y double prime. Plus 2x times x minus 1 squared y prime. Plus 3 times y. Right? That's what it is. And since we're looking for powers of x minus 1, this 1 plus x is a little bit, it's not in the right form. We like to have something like x minus 1. So let me just put it in over here. 1 plus x is equal to 2 plus x minus 1. So I can replace 1 plus x with 2 plus x minus 1, because 2 minus 1 is 1. But this is clever, but necessary. So now when I expand this, let's see what I get. Also, x, here I have an x. X is 1 plus x minus 1. Okay. All right. Let me just go back a second and just start this process again. So I want to make it a little bit clear, as clear as I can, what's going on. We start with an expression like this. Suppose we actually had a differential equation. And we wanted to solve this equation equals 0. So we don't know what a solution is, and we can look for a power series solution. So here we take a power series in Y, and we're looking for a solution centered around the point, around the number 1. This is a power series in x minus 1. So our problem is to find a solution of this differential equation, which is defined on some interval, some open interval around the number 1 that includes the number 1. So we're going to look for power series in x minus 1. There's the power series. This is the first derivative. This is the second derivative. So I'm going to plug these power series into this equation, or into the left-hand side, right, and collect the terms. I want to write this as a power series. So I have 1 plus x, y double prime. This is y double prime. And 1 plus x is 2 plus x minus 1. So just this is 2 times this, plus x minus 1 times this. When I multiply x minus 1 to the n minus 2 by x minus 1, I get x minus 1 to the n minus 1. Oh, sorry. This is just 2 times x minus 1 squared. I don't need that. Plus 2 times x minus 1 squared times y double prime. So that's plus 2. What is y prime? Summation 1 to infinity. N a sub n, x minus 1 to the n minus 1. Then I'm multiplying it by x minus 1 squared. So n minus 1 plus 2 becomes n plus 1. Plus 3 summation a n x to the n. And now I want to shift my indices so everything, so I only have powers of x minus 1 to the n. So for example, here, if I replace n minus 2 by n, or n by n plus 2, I get summation 2, n plus 2, n plus 1, a sub n plus 2, x minus 1 to the n, right? And goes from 0 to infinity. Right? Whatever is the coefficient of x minus 1, this is 2 greater and 1 greater. That's exactly that. And here I want to shift down by 1. So this is summation. If I replace n by n plus 1, I get n plus 1 n, a sub n plus 1, x minus 1 to the n, and goes from 1 or 0, when n equals 0, just get 0 to infinity, plus this. Plus this, sorry. Here I want to replace n plus 1 by n, so I want to replace n by n minus 1. I get summation 2 n minus 1 a sub n minus 1 x minus 1 to the n. And the first term of this, when n equals 1, is a1 x minus 1 squared. So here n goes from 2 to infinity. Plus this last term. And we just need to collect the terms. Yeah. So you really, again, I can't emphasize strongly enough that there's a lot of algebraic technique involved in being able to work with power series. And okay. All right, so let's move on to actually trying to solve some differential equations. So we might have a second order linear. Let's start with homogeneous. So P0 of x y double prime plus P1 of x y prime plus P2 of x y equals 0. And normally what we want to do is divide by P0 of x. So we have the leading coefficient. The coefficient of y double prime is 1. But of course, you can't divide by 0. So suppose what we want is to find the solution of this differential equation on some interval around a point x0 on the number line. So in the good case, P0 evaluated at x0 is different from 0, and you can divide by it. In that case, x naught is called an ordinary point. The alternative is P naught of x naught equals 0. It does equal 0. So in that case, x naught is what is called a singular point. And that's more complicated. So we're going to start with the easy case when x naught is an ordinary point and we can divide. So oh, and I want to say, in our beginning study of differential equations, these functions P naught, P1, P2, these are polynomials. So they're not exponentials or logs or anything, they're just polynomials. So that is relatively straightforward. And if you were to divide by P naught of x, you get y double prime plus P1 of x over P naught of x, y prime plus P2 of x over P naught of x, y equals 0. So the basic theorem has to tell us something about when such a differential equation has a solution. And the theorem says that if these polynomials P0, P1, P2 have no common factor, and P naught at x naught is different from 0, so x naught is an ordinary point, then this differential equation always has a solution as a power series. And sometimes we introduce the following additional bit of notation. So if we're looking at a differential equation like this, we just define what is sometimes called an operator, a linear operator, Ly. So Ly means P0 of x, y double prime, plus P1 of x, y prime, plus P2 of x, y. And we want to solve the differential equation Ly equals 0. And there will be a solution where y is some power series. Well, some power series. An x minus x naught to the n goes from 0 to infinity. So let's look at a nice example, which is an example where we already know the answer. Suppose we have the differential equation y double prime plus y equals 0. So Ly is y double prime plus y. And we want a solution centered around some point x naught. So we want to find y summation an x minus x naught to the n. N goes from 0 to infinity. So y double prime, if we differentiate this twice, we get summation n minus 1 an x minus x naught to the n minus 2, which is the same as summation n goes from 0 to infinity, n plus 2, n plus 1, a sub n, x minus x naught, a sub n plus 2, n plus 2, n plus 1, a sub n plus 2, x minus x naught to the n. So I'm going to give you a couple of minutes to work on this yourselves. Here we have y double prime, here we have y. Plug it into this differential equation, collect the terms, and see if you can find some recurrence for the coefficients a sub n. So we'll just take a couple of minutes and I will pause this recording. And I want you to try to do that. If we're looking at this differential equation, by the way, without power series, you can certainly tell me what the solutions are, I hope. What are the solutions of this differential equation? I mean, it is a differential equation, second order homogeneous with constant coefficients. So if you write down the quadratic equation connected with this, it's r squared plus 1 equals 0. So r squared is minus 1, or r is plus or minus I, which means two solutions of this equation are y1 equals cosine x and y2 equals sine x. Or if you wanted the solution centered around a point x naught, it could be y1 is cosine of x minus x naught and y2 is sine of x minus x naught. So before you even start, you know what the solutions of this differential equation are. And what we're doing is trying to find a way to express those solutions as power series. So this is an easy equation because you know the answer before you even start. But let's look at the power series solution. Here's y. Here's the second derivative, y double prime. So y double prime plus y prime figure it out. Y double prime, sorry, y double prime plus y is summation and goes from 0 to infinity. What is the coefficient of x minus x naught to the n? In y double prime, it's n plus 2, n plus 1, a sub n plus 2. And in y, the coefficient of x minus x naught to the n is just a sub n. So this is the power series, and we want this to be 0, which means all the coefficients have to be 0. n plus 2, n plus 1, an plus 2, plus an is 0. Or you can write an plus 2 in terms of an plus 2 is minus n plus 2, is minus an divided by n plus 2 times n plus 1. So for any value of a0, this determines a2 determines a4, and so forth. And similarly, for any value of a1, this determines a3, a5, and so forth. So let's actually start to compute these coefficients, right? So this is our recursion relation. An plus 2 is minus an over n plus 2, n plus 1. So given a0, a2 is minus, see, when n is equal to 0, you get a0 over 2 times 1. A4 is minus a2 over 4 times 3, which is minus a0 over 2 times 1 over 4 times 3 is plus a0 over 4 times 3 times 2 times 1, or a0 over 4 factorial. This is minus a0 over 2 factorial. A6 is minus 1 over 6 times 5 times a0 over 4 factorial. That's minus a0 over 6 factorial. And you should recognize a pattern. It looks like a2n, this is for even numbers, a2n is going to be plus or minus 1 times an a0 over 2n factorial. And this is minus when n is odd, and even, and plus 1 when n is even, right? So for example, when n is 3, you get a minus. When n is 2, you get a plus. You get this relation for a sub 2n. So you get one solution that involves even powers of n. What about this relationship when n is odd? Let me do it over here, n odd. So this is for n even, or this is for even subscripts. A3 is minus a1 over 3 times 2, which is minus 1 to the 1, a1 over 3 factorial. A5 is minus a3 over 5 times 4, which is plus over 5 factorial. And in general, a sub 2n plus 1, these odd coefficients, you're going to have a 2n plus 1 factorial in the denominator, a minus 1 to n in the numerator times a1. So what we get is, for the general solution of our differential equation, y double prime plus y equals 0, we get a solution y, which is summation n goes from 0 to infinity. For the even powers of n, minus 1 to the n, there's an a naught I can take outside, over 2n factorial, x minus x naught to the n, plus a1 summation n goes from 0 to infinity, minus 1 to the n, 2n factorial. This would be x to the 2n, x minus x naught to the 2n minus 1. I'm sorry, 2n plus 1. I'm starting with 0. Yeah. And you might remember from calculus, but probably you didn't cover this, though you were supposed to. This is exactly the Taylor series for cosine of x minus x naught. And this is exactly the Taylor series for the sine of x minus x naught. So we recover the cosine and the sine as the solutions of this equation. And we see that every solution of this equation is this linear combination of the cosine and the sine. Okay. So what I'm looking at now is the very beginning of section 7.2. And I'm going to stop at this point because you really need to be able to spend a significant number of hours really working through the textbook and studying this material and looking at the problems. So this is not trivial stuff, and it takes a fair amount of work to understand it. Okay. Any questions at this point? I mean, I encourage you to spend as much time as you can over the weekend, that is between now and next Monday, studying this material on power series and this very first example of finding a power series solution to a differential equation. And hopefully you'll be able to ask me some questions next Monday. Okay. All right. If there are no questions, we will stop right now. Be well.